of a little mini Frankenstein, because it kind of, it's a good Frankenstein. It's not a mean one that's going to go, run amok in the village. It's more of the singing, dancing one from Mel Brooks.
How big is your bench set up right now? If you were to set up like using your heart avatar.
So I actually brought a heart show and tell. So I'm going to pull that out real quick. So this setup is, and you can come up and take a look at it. I'd rather not pass it around because it's a little delicate here and there. But this is a setup. It's about the size of a shoebox, and we have 2 pumps to run it. One pump does run a cardiac assist because the cells are not strong enough to pump fluid throughout all of the other organs on their own. And also the cells behave better when we have a cardiac assist on them. And so, the organ is milliscale, which means it's about 1,000th of the size of our heart. And it is run by a shoebox sized thing. I really think that our life support system is fantastic, and our fluidics guys are great. Because when you look at some other teams running organs, they have these big pumps that are this big in the lab running things. And the nice thing I think about Lanels is that they're really, really small. One of our fluidics guys also used these pumps to help make smaller vacuums that could be portable for battlefield mass spectrometry or things like that. When I asked our fluidics guy about making the lung platform, I asked him, I said, I want an iron lung. And he said, what's an iron lung? He grew up in a different country where he wasn't aware of the polio epidemic of the 40s and 50s. And I showed him pictures of an iron lung on the internet and said, our lung functions by our muscles pulling down. Our diaphragm pulls down, our rib cage expands, it makes a vacuum, and air flows into our lung naturally. And so he thought about it and thought about it and made me a shoebox-sized iron lung for our lung, which was really very, very neat. So all of our organs are about shoebox size like this, and you're welcome to come up and take a look. I just didn't want to pass it around because it is a little bit finicky.
So what are some of the other areas of expertise that has grown up here at the lab that enables you to do this work? I mean, it really is, kind of takes a village, it seems. So what are some of the other, like fluidics probably is part of it?
So we do have a really good fluidics team here. Omar is part of that. He's in the middle there. The leader on that team couldn't make it tonight because his wife's been ill. But we have a fabulous fluidics team out of physics division that helps us with that. The team lead, or the project lead, is Rashi Iyer, who is out of A division. And a lot of us are in bioscience. So it really is this, mishmash of different skills. And I think part of it is just being open to different ideas. I'm not trained as an engineer. I'm trained as a biologist, as a biomedical scientist. But my dad was an engineer, and when I was a kid, he was always telling me, well, how do you think that works? And I'd have to answer it. And he said, well, let's take it apart and see how it works. And so I guess I had my engineering training very young instead of at the university. And Tumpa is a bioengineer. Omar, who is on our engineering and bio team, he has a biology degree, a master's in public health, and his dad trained him as a car mechanic.
Wow.
So I think, I mean, in order to make things like this, it takes more than what you learned in school. It also takes a lot of what you learned in life. I'm gonna just put this down.
Oh, let's go.
Yes, ma'am.
What do stem cells cost?
So the ones for the heart, they're not cheap. They are, I want to say $2,000 for 1 million.
Okay.
And 1 million cells fits in about my pinky finger. So they're not cheap. But the people who developed what they're doing, and they don't divide either. They do divide when they're stem cells, but once they sell them to you as differentiated heart cells, they do not divide anymore. And so I don't begrudge the company that sells them to us for this, because they are doing great service. I think also, you know, if their research continues on how they can make these cells better, maybe they can make me a new heart someday.
Right.
Yeah.
So I assume they have to harvest a lot of skin. That's why you use a deceased donor to get that little bit of stem cell out?
So for the stem cells, once they have the initial stem cell, it keeps dividing.
Oh.
And that's good. They have
So why can't you use a
their dividing stuff. They sell the stuff that's been differentiated and won't divide anymore, and that's how they make their money. Now with the other tissue we use, like the lung cells, that is fresh, and that is actually a very big job for people to dissect a lung and harvest out the cells that are in the branches or in the trachea or in the alveoli. So some of our organs, like the heart, are made with adult-derived stem cells. Some of the other organs are made with fresh or fresh frozen cells. And yes, it does take a lot. Like the liver takes about 40 million cells, I think. But those are a little less expensive. Those are like $70 a million.
Do they have that many customers to drive the price down like that?
For liver cells, yes, because pharmaceutical companies will buy liver cells in spades and test all sorts of precursor compounds that they think might be useful. And that's a good use of them, I think. You know, narrow down some of the possibilities.
Anyone else? I think we're right near the end. Well, let's all thank Jennifer.
You guys are great, thanks.
If anyone is interested in Bradbury Science Museum Association membership, please come up and see us. Thank you very much.